Hi, and welcome to LCU14-311. So this is Advanced Toolchain Usage Part 2. This is a continuation of Part 1. If you missed Part 1, you can watch Part 2 and then go back and watch Part 1 via the Zarista link that has the archive presentation. So this is a continuation, so there's not going to be an introduction. Will is just going to pick up where we left off. If you would like to follow along on the Etherpad, please go to the previous notes section, and then you'll find a link to the LCU 14-311 presentation, which is this one. The video link is delayed about 40 seconds. We have had some online participation, so if you're online and you want to participate, please put your questions in. I'll be watching the Etherpad, and then I will have Will and the others answer the questions as they come up. So if you're in the room, for the benefit of the online audience, please raise your hand. We'll get a mic to you, and you can ask your questions via the mic. All right, so Will can take over. Oh, the trackpad doesn't work, Will.
Yeah, it's okay. Yeah. Right. Well, I'd like to cover a little bit about feedback-directed optimization, which is also known as profile-guided optimization. The distinction seems to be that profile-guided optimization is using gprof-style code instrumentation, and feedback-directed optimization is the catch-all term for both methods of doing it. Feedback-directed optimization uses runs of programs to collect information which is fed back into the compiler to improve optimization decisions. In GCC, it affects branch probabilities, inlining decisions, and can affect reordering of code into hot and cold portions and partitioning the code. But this doesn't actually work on ARM, and following discussions this morning, it may not actually work on AR64 either, the actual partitioning part. But you still do get good improvements on the other portions of it. There's two ways that the profile information can be generated. The standard historical.
There's also value directed. Yeah. There's also value ones. So there's like if the most common is a divide by a power of 2, it will get rid of the divide and optimize it such that it's just a shift. And there's a few other value ones.
Yeah, so the traditional GCC method has been to use a gprof-style instrumentation of the code, which adds instrumentation to each basic block and how many times it's entered, etc. Dumps that to a file which you can then feed back into GCC. And there's now a more modern method, which is to use perf or some other statistical method to sample hardware counters and generate a statistical profile and figure out how likely each block is. The gprof style is more accurate, but it is going to be slower because you've got to instrument your code, and it also involves building your code multiple times. So to turn on code instrumentation, you need fprofile generate, which then, when you run an application, will start outputting profile data into the directory specified. It's worth knowing at this point that really the workload that you run your application with is critical to this actually working properly. Because if you have a very good representative workload, then you're going to get great improvements. If you over-optimize for a desperately simple case, then you may not see improvements in production. It may actually make your code worse. Then you have to pull fprofile use on a second run of the compiler to pull that profile information in and make the new optimization decisions. obviously this means you have to build your code twice, which is kind of a deal breaker for some people because it's quite a lot of build system machinery needs doing, and it doesn't really lend itself to quick edit compile cycles.
Doesn't work on AR64 at the moment?
In theory, we think it may not do the partitioning stuff. The partitioning stuff disabled on ARM, but I discussed this with Romana this morning, and he suggested that the partitioning may not work on AR64 either. It's just nobody's actually disabled it. And it may only be a theoretical issue because it's to do with branch distance, so it may be safe for most stuff because the branch distance is like 128 meg on AR64. So.
Actually, it should use long branches. It has a mechanism to use long branches, so it should be able to easily fixed.
Yeah.
The problem with ARM32 is it actually has to do with the unwinding tables.
Oh, I thought it was literal pools. But
Well, it's mostly doing with the unwinding tables, which is not exactly detailed enough, since they want to compress them everything, and it's different than the standard GCC are unwinding tables and everything.
Yeah. Right, so I ran a few quick tests on my laptop, which isn't ARM, unfortunately, using the Opus encoder test. And as you can see, it takes about 27 seconds with just O2. If you've pulled fprofile generate, it pushes the runtime up to 34 seconds because that's adding the overhead of instrumenting each and every basic block and collecting all those profile details. But then afterwards, when we actually pull the profile back in, then it gives us a quite nice speed up of about 12%. This isn't really a representative example. But it shows that the improvements can be there if you have a workload that, I mean, this is obviously the same workload twice in a row, so all the decisions will have been pretty much perfect.
Yeah, so my rule of thumb is if your application profile is accurate, so whatever you test workload you run is representative of what the application is actually doing, then about 5% is expected performance improvement.
Yeah, that sounds like a pretty good ballpark figure. A few numbers as well of build time, because I mean this is a pretty small project, but if you're building some huge C++ application, this can become something of a deal breaker. Both the instrumented build and the optimized build will take significantly longer to do because they're just that much more complex. Which is actually something with the optimization levels that I meant to ask you about was how long will it take? Auto-FDO is the statistical profile sampling method of doing this. It was developed by Google, so it's not available, as far as I'm aware, in GCC Master. It's certainly not under the narrow toolchains. It uses perf to get a statistical profile and figure out sort of whereabouts you spend plenty of time in your code. And then there's a conversion tool that will turn that perf profile into something that GCC can actually import. It is supported, I believe. Renato's not here, is he? In LVM, but we'll gloss over that because Renato's not here. The performance isn't as good as the instrumentation method in the final executable. It's said to provide about 70 to 80% of the performance improvements, but it does save you the task of having to build an instrumented build, so you can actually run this on production software rather than having something that runs much slower. So Google are obviously using this on their production web stuff.
Yes, there's a question here, so I might as well address it. Down here in line 18.
Well,
Are there any optimizations in this category for paging stroke TLB hits or miss? Not that I'm aware of. I guess the two things there, you've got code size and then you've got some kind of horrendous bin packing problem if you try to put stuff in pages. But
so there is nothing for TLBs. Since so prefetching, but prefetching usually, so sometimes actually loop prefetch arrays you could do using profile, but prefetching actually, the way that it's implemented in the architectures, it actually does not cause a TLB miss. So that doesn't fix the problem there. Usually, the way that people have started now working around this issue is have the kernel do large page support transparently.
Yeah.
So, and then you don't have the worry about, the extra TLB misses.
Yeah, I mean the hot cold partitioning should help with locality, which will help with TLB misses.
On the iCache side.
Yeah.
Not on the data side.
Sure.
The iCache side, yes, it will help, but on the iTLB side, it will help, or the iCache miss side. But in the data side, the only thing is loop prefetch arrays for right now, and that doesn't affect TLBs, but that definitely affects the caches.
Well, so if it's a TLB miss, the prefetch is just dropped.
Yes, and that's standard across almost all, not just ARM, but every target that has ever worked, because a TLB miss is pretty high.
No, it's hard to. I think.
I don't know.
Whether
So
the
it's
transparent
whether
huge pages.
yeah.
It should be supported on pretty much anything that has a variable page size.
Well, you actually it has to be implemented. I don't know where.
It's not a vast amount of work. I would expect it to exist. I couldn't say for sure, but I would expect it.
Yeah, it exists right now. From what I know, it exists on x86, MIPS, and AR64. I don't know ARM64. I don't know if it was added for ARM32 yet. I haven't looked into the kernel side of that. But, of course, we're toolchain guys, not the kernel guys. If members are interested in that, there's another team that you could probe and try to force that issue.
Who's doing LTO?
I apologize. I didn't realize you were sorry. Okay. How many of you are familiar with link time optimizations in the compiler? So maybe about a third of them. Okay, so I'll give just a really brief overview. In general, as I had mentioned earlier, yes?
So how many of you have actually done a link compile with LTO of a project?
Okay.
Okay.
Okay. So in general, as I was saying earlier, most C compilers don't have visibility into other files, right? So let's say you've got a.c, a.cpp, but you're calling something in another file. It doesn't have visibility, or there's a global variable in another file. In general, you can play tricks with inlining and other things, but in general, the compiler doesn't have visibility. LTO gives the compiler visibility. So what happens is, if you specify the -f LTO option, essentially what happens is that the compiler puts intermediate language into the object files, okay? And then it gathers everything together at link time. That's why we're calling it link time optimization. And now the compiler can do the traditional optimizations that it would typically do within a function across your entire program. So this is really true whole program optimization. And if everything goes okay, and in most cases, the compiler can make better decisions. It can potentially inline better, cloning, better analysis, things like that, alias analysis. So in theory, it should make your program better. So one important thing that you want to do is you want to make sure that you compile with the same options on all of your C programs. It's not an absolute requirement, but in general, it's probably better. So if you're going to do O2, stick with -O2, okay? Because
-O2 at -FLTO.
Yes, exactly. -O2 and -FLTO. Because the compiler still has to optimize the individual file, and then you're going to do your link time optimization step later. Anything else on here? It is enabled in GCC 4.9, and it is part of the neural toolchains. So I would definitely suggest giving it a try. If you need to squeeze a little bit more performance out of your application, you may want to try and give LTO a try. Any questions on LTO?
So I have a note,
Yes.
probably just in case. I'm not sure whether that's a requirement or not.
Yeah.
On the link option, also put -O2 -FLTO, so that the compilation lines are exactly the same everywhere.
Wow.
Link, but there is no -O2.
Yeah, there's no -O2.
You need O2.
Oh, you do need the O2 on the link line. Okay.
Oh yeah.
Okay.
You need to use O2
Okay.
on the link line because
As well.
otherwise you get zero code.
Okay. All right. All right. Any questions on link time optimization? Okay. Oh, you do have a question.
I was speaking to Christoph about this, and he suggests that LTO and PGO are very complementary. So that's probably something to look at. And I was wondering if you had any time to look into how long the link times were and how much memory they used.
I mean, in general, from what I've seen, I mean, you're going to use, I know when LTO first came out, it was pretty prohibitive. I don't know, I mean, I know that they have it so that it is reasonable now, but, it's going to be directly proportional to the size of your application, so.
Yeah. So,
But I don't know if the sizes are off the top of my head.
Actually, it depends because they've done, so there's been quite a stuff. So with GCC LTO, it's not really exactly LTO. It doesn't combine everything into one, well, kind of does. But it so there's a couple phases what it does. So first off, when it generates the LTO information, it generates some summaries that then goes, and so when the linker comes in and sees that the symbol is needed, it asks the plugin to go and sets up a few things. And then the plugin then calls GCC again with some options, internal options obviously. And so GCC then decides, okay, we have these files that we have the objects from. And we're going to take, then it decides what to inline and everything from those summaries. And then it rewrites the object files again with the LTL information. And then at the very end is when it starts out doing the actual compilation. And so the memory usage is much less than if you just combined everything, merged everything into one object file, and then loaded it up into memory. There has been quite a few improvements for 4.9, and I think there's more for 5 that for memory usage. If you, Jan Hubika has quite a few nice blog entries on the memory usage in GCC versus LVM a little bit, just because he wanted to compare. He's done for Chrome I think Firefox, for an example. So there's actually graphs of how much memory is used and not over time, but with certain options and everything.
So when Andrew says that LTO GC does not quite combine, in my opinion, GC's LTO is better than traditional LTO in that sense that it is designed for production size applications. So it does LTO to the point that it is capable of handling very, very, very large projects in very reasonable amount of time and very reasonable amount of sizes of RAM usage. So there is no real excuse not to try it.
I think this was the only slide on LTO. Yep. So inline assembly.
So inline assembly. Traditionally, if you want your code to have a very specific assembly instruction, you would do it in line assembly. For the most part, all the common use cases, such as CMD instructions, have their own built-ins. So never use inline assembly if there is an alternative way, like you use a built-in, use intrinsic, but there is still a reasonable a couple of cases when you have to use inline assembly. If you're writing a C library, then you definitely will see some. You will have to write some assembly because you have to call system calls, and compiler will never generate those. If you're writing a hypervisor, compiler will not generate. Compiler does not have any built-ins for privilege code instructions, I believe. And GC supports, in those cases, you have to use inline assembly.
Another one is any system registers.
Any system registers.
Or coprocessor registers in ARch32, if you need to use them.
Yeah. Normally, you would do that in a C library.
Yes, there are a few. One example, at least in ARch64, is page line size, or grabbing, or for example, is userland perf counters, reader.
Yeah. So GC supports two flavors: basic flavor, Basic Asm, which I didn't know about until this presentation, and extended Asm. This is what is used by Linux kernel, by glibc, and by most other projects that have inline assembly in them. For Basic Asm, we will touch only on this slide. It allows you to emit a single instruction in inline assembly. Say again? Yeah, this one will help you with named registers. But you cannot pass any parameters from C code. You cannot get output results into C code from Basic Asm. For extended assembly, you can do that. And it has 4 parts: template, outputs, inputs, and clubbers. Template is the actual assembly you're writing. It has special syntax for denoting arguments and inputs and outputs. It can span multiple instructions. glibc has inline assembly pages of inline assembly code, so it does not have to be short. It can be as long as you want it to be. Contrary to many other compilers, GC and LLVM treat Asm as just another statement. This is not a reset point for the compiler at which compiler forgets everything about memory aliasing, it forgets everything about variables, values in the registers. It does not. So for GC and LLVM, ASM inline assembly is just another statement. Nothing more, nothing less. It optimizes across, it optimizes code across assembly statements. It can optimize individual assembly statements. So if you have two assembly statements which are identical and which have exactly the same inputs and outputs, in theory, GC can remove the second of them because it would be just a duplicate calculation. To be able to do that, GC has to know about all effects of inline assembly statements. Whether it touches memory, whether it touches conditional code register, whether it branches somewhere, whether it changes memory, or whether it changes state of processor. If you have something like an instruction which changes configuration of the system, like, let's say, precision of floating point unit, then you have to specify that assembly statement. It is still possible to make assembly statement a reset point for a compiler. It's just not by default. And a point on volatile keyword in assembly statements. Volatile makes it sure that assembly statements is not removed normally. What it guarantees is that the number of executions of that assembly statement will be always the same. So that if you have ASM volatile inside if 0 clause, so if it is if 0, then GC can see that that ASM volatile statement will never execute and it might delete it. Otherwise, if ASM volatile statement has same inputs, has same outputs, but still there are two executions of that statement, even though the statements are completely identical, GC will keep both. That's the effect of ASM volatile word. Do you have a comment?
Yeah, I have a question. Is there any sanity or bounds checking for inline ASM statements in GCC? And then likewise for LLVM?
For GCC, sanity
or type checking, rather.
And bounds checking is performed on the arguments. So you can think of ASM as kind of ASM parameters as in the same sense as parameters for a function call. So GC would do bounds checking on the parameters, but it will not look inside the template, the assembly statement template.
What about on the return type?
But for a return type,
no, it doesn't.
Ideally, yeah.
The other thing is, I think there is some undefined sanitizer or memory sanitizer that's being looked into adding support for the bounds checking, and I think LLVM already has it. For an example, I think the memory sanitizer already has the inline assembly support.
I don't know.
Okay, you don't know. Okay, but there was looking into that for memory sanitizer to read and write, checking to make sure you're able to read and write for that.
I guess the only thing I would say in terms of sanity or bounds checking, be really careful when you're using the basic ASM, when you're not specifying any operands, because you might specify a specific register, and especially if it's one of the registers that the compiler is going to use. I mean, you should never, ever do that. Yeah. I mean, or if you do, you really need to specify in the outputs or what's clobbered. So.
Okay, and
I just had one further comment on that. I've gotten bit in the past on not properly specifying the return type, and so just getting truncated values, and you get no warning, and it's just impossible to find except for runtime errors.
And one more thing, I'm trying to remember. Memory clobbers, make sure, that's I'm going to say memory clobbers, memory clobbers, memory clobbers. Even if you don't even if you don't think that you have your other constraints correctly, sometimes you don't. And if you read from memory or write to memory, just add the memory clobber.
If you read from memory? No.
Yes, there's a reason behind that.
Why?
If your constraints are such that that you only pass the address using the OR constraint, and that if you just pass the register, you pass the address via just the OR constraint, GCC has no way of knowing that that's going to be used in any way except as arithmetic. So using it, if you read it, sometimes use the memory constraint, just to double check on the constraints.
I think if you're passing a pointer as argument to inline assembly, then GCC will assume
no, that's not how it's implemented. It's implemented that it assumes nothing. It assumes that it's just an argument.
Right. Yeah. So I worked around this problem is that I just added a second input argument, which was the reference to the memory through that pointer.
And so the other one is memory constraint. That's why I was saying memory constraint, memory constraint, memory constraint.
Memory clobber.
Memory clobber,
memory clobber.
Yes.
So either do memory clobber or make sure that in your inputs you have all the memory locations referenced that inline assembly would read or write. More on the inline assembly variables. So that the example code just several weeks ago. Function starts. We know, engineer knows the ABI, great, that the arg, the only parameter, the function argument, is passed in register 0. So he is using just assembly with instruction referencing that register and assuming that data will be there. It might not be. Very well might not be. Because treat this just like any other race condition between programmer and compiler. Compiler will put something in here, which will clobber the R0, or it would just move it to stack. It might do that, especially if you are compiling without any optimizations. Compiler does not care where the argument is. So it might split it to stack and have register R01, R0 for something else. The correct way is to specifically assign argument to register variable and specify R0 as the register to hold that variable. So in this case, it is guaranteed that R0 will hold the value of this variable, which will coincide by the set statement to be the same value as argument to the function.
He's correct.
In this example, the Asm R0 or the arc, you can remove it because you're not using this. If you are hard coding the R0 inside the template without %0, then it would make sense, but usually
It does. So this is if you assume that instruction always have to have not just any register of not just any general register as its argument, but exactly R0. So this is the pattern, the exact pattern that's used in glib for system calls, where where parameters to a system calls are passed in specific registers.
So you could put R0 there instead of %0?
Yes, it's possible.
But it's not really...
This is just linear.
It's not really that elegant in the sense that you basically say above that it's in R0, and then in the what's it called, the inline assembly string, you basically say %0 to make sure that you know for a fact that you're using this register, and then you have to go back to make sure that it's in the right register.
And also, if in maintenance or in future revisions of your code, you add yet another argument to your function, but still just add some more logic to that function and change arguments order. In this case, it's a general solution which will always ensure that as inline assembly is passed data in the right register. Okay, auto-vectorization, and I think this is going to be the last topic.
Okay, just one question. Where are the constraints documented for inline Asm?
Constraints for inline Asm are documented in GCC manual, but they are mostly designed by GC developers for GC developers. And the fact that users can use them is a happy coincidence. So use bulletins. So bulletins is a very user-friendly feature. Inline assembly is not a very user-friendly feature.
Well, while Will's getting ready, there's another question. Are there any specific LTO performance improvement numbers that can be shared?
No. No, there aren't any generic improvements. It's application dependent. It really is.
Okay.
To answer the question about memory usage, LLVM uses a quarter of the memory.
Right.
Right.
Without LTO, LLVM uses a quarter to a third of the memory that GCC uses, but with LTO, it's twice as much. Yep.
Yeah.
It's an explosion.
Yeah, that's why I said that LTO for GCC, I know they've improved it quite a bit.
So, but that's 3.4, which is like 6 months.
Okay.
And there's a lot of LTO stuff going on.
Yes, and it's same with GCC. There's a lot of LTO, and I think Jan Hubika's blog actually has been up. No, I think he's got a recent one. So I think there was some comments about updating the slides again, those graphs. So basically, that might be 6 months ago.
And the binary size is not perfectly the same.
Yeah. And I think performance I think he ran some performance testing too.
Yeah.
So, but that's why I said Jan Hubika's blog has a good thing. About the LTO question, for performance, there's, I've seen spec give about 5%, 5-10%. I've seen it degrade a little bit for some benchmarks. I've seen it improve. I've heard, from some customers where it improves it like 20 to 30%.
So LLVM is better than GC 4.7, GC 4.8.
Right. Yeah.
Yeah.
Yeah. It does this.
Yeah.
Goes back and forth. Yeah. Go on.
Okay.
Vectorization is a good way to speed up your code. It generally operates on repeated sequences, typically loops, using vector instructions, which on ARM will be neon, which are SIMD instructions and can do more than one operation per clock. To turn this stuff on in GCC, you need O3 or f-tree-vectorize, but as Maxim said, don't use f-tree-vectorize, use O3. So I've got a simple example here that just takes a couple of arrays of double values. It's a fixed size, which is kind of a nice little cheat just to make things simpler, and it adds one of the arrays to the other. So this is the output from GCC with fairly basic flags, and annoyingly it uses the old mnemonics for the instructions. So if you look in the ARM manuals, you won't find any of those instructions in it. Well, any of the floating point instructions. They've all changed. But apparently I'm told that's fixed in master now, so Kirill fixed it apparently. Oh, he submitted a patch. I don't know if it's gone in.
Patch.
Yeah.
There's a patch to do.
Yeah. So I mean, we can see it's doing a load, it's doing an add, and then it's incrementing a loop counter, doing a compare, and then storing the result.
65,000 times.
Yeah.
64K.
Yeah. I mean, that obviously could be better because we want to vectorize that. We want to see instructions with V's on the front, basically. So pull O3, and this should turn on vectorizing. But it actually doesn't do anything with this example. So to figure out why the vectorizer isn't working, there's a flag called f-tree-vectorizer-verbose, which will dump. It takes its f-tree-vectorizer-verbose equals number, and then a verbosity level, which is kind of tricky to figure out exactly what level you need. I think I use 5. But one of the things that it will spit out is saying no vec type for statement, this thing, scalar type double, which what this is saying is that on ARM v7 AArch32, Neon doesn't support doing double precision vector ops. So this just isn't going to work. So switching to float by just basically setting the code, switch double to float, still doesn't vectorize the thing. So the verbose now is outputting bad operation or unsupported loop bound, which is clearly saying that Neon doesn't support full IEEE. So this is the issue that Andrew brought up earlier, which is that Neon does some little tricks to basically simplify things. It doesn't handle nans, denormals, signaling exceptions, I think, of the main things it doesn't support. So we can, it's a big assumption, but if we assume that we don't have any of these things in our code, we don't care. Most people, generally nobody cares about traps. Nobody traps, ever. Denormals, nans you might see. But you can turn this off with F-unsafe math optimizations, and GCC will now get some vector instructions. The vector instructions are these ones with V's in the middle. But you can see there's also some floating point instructions, which is very similar to the code we had originally. And that's because this bit here is looking at whether or not whether or not the two buffers overlap. And depending on whether or not it thinks it's safe to jump into the vector loop, it'll do the vector loop. If it doesn't think it's safe, it'll do the initial code that we had before. So
in the original code, the original instructions on double registers, this one is are in
single registers. Switch to float because otherwise.
Oh yes.
Oh, we've had to stop on paper. Okay, so the restrict keyword is a really neat thing that basically tells the compiler that these two pointers cannot ever alias. So they can never be pointing at the same memory, so you don't need to worry about copies overwriting each other. So this should make things much simpler, and the compiler behave a lot better.
Beautiful.
And you can't read that, but then it doesn't really matter, because basically you can see there's 1, 2, 3, 4, 5, at least 5 columns of dense stuff there, and it's pretty hard to figure out what any of it's actually doing. But it doesn't really seem what we wanted, which was a tight vectorized loop. Essentially what that was trying to do was it was trying to figure out whether or not the pointers were sufficiently aligned that it could do a full-size vector op. We could use some kind of type tricks or something, but you can also use built-in assume aligned, which will tell GCC, assume that these buffers are aligned. And if you're using malloc, then chances are that they already are aligned, so you may get this practically for free by just putting these. I don't know if there's a better way to do that other than using the intrinsics.
And also, by the way, that was added in 4.9.
All right.
Those built-in assume aligned.
Okay, that's good to know. Always be on the cutting edge. Pace. So that's what happens once we tell it about the alignment, which looks pretty good. I don't think there's really much we could do better than that. It's doing 2 pairs each time. So, yeah.
And also incremental.
Sorry?
Also incremental updates.
Yeah. So yeah, that's pretty much what we wanted in the beginning. So it's kind of tricky to get the vectorizer to do exactly what you want, but f-tree-vectorizer-verbose is your friend. So a few little sort of hints. Right types, obviously, if you actually want to do operations on shorts, use shorts. Don't use ints, because otherwise you're going to use the wrong kind of ops. You've got to understand that where floating point is concerned, Neon does have a few drawbacks, but most of the time you probably don't mind. Restrict annotations are great. They'll tell you, they'll tell the compiler it can do a lot of things that it wouldn't otherwise. Alignment's great. Loop conditions, that was a very simple loop using a constant, which is slightly cheating, but as long as your loop conditions are simple and GCC can analyze them easily, which is generally if you do like for I equals 0 to n, that kind of thing will do well. If you have something more complex, not so much. Things like breaks and function calls in the loop, anything that there's any complex flow control, it's probably going to stop it happening as well. And yeah, f-tree-vectorizer-verbose, where you want to look.
Okay, a couple of questions here. So, does vectorization work for integer types or only for floating point types?
Yes, it does work for integer types. I'm not sure of the full gamut of types that are supported, but certainly floats in shorts.
And how much time did it take you to get from initial non-vectorized version for that simple loop down to the final? So,
Less than an hour.
Less than an hour for a loop.
Yeah. And I've never done this before.
So, GCC vectorizers also address some standard library calls.
Yes.
Those that has vectorized version. So you can call whatever.
Well, I can answer that. There's no vectorized library as of right now, but well, for AR64, there's some instructions which are like, so round, I think there's a vector version. There's a vector version of square root, and a few other ones. So you can use the instructions. Right. So I'm trying to remember. Square root's done. Byte swap is done. So if you have a loop that does a lot of byte swaps, it will be vectorized.
It's worth knowing as well that AR64's got a richer set of
Yes.
operations.
Yes. So I don't know the exact details of
Like it will be
ARM32
doubles.
versus ARM64. So I'm just going from my experience with AR64.
The other thing that GCC can do, and I can also is stripe vectorizer.
Yes, stride is happening. And oh, so something that's not mentioned here is we can also vectorize outside of loops. Yes, SLP, which is not mentioned. You haven't mentioned it yet, but the other thing is that's also not mentioned is that you can actually vectorize some code without using even the neon registers. So if you have if you're loading up chars and you're doing a loop of chars and doing it ORs or some other things, GCC vectorizer actually will vectorize that into integers, larger sizes, not necessarily using the vector unit. So that's something that the vectorizer will also do.
So I have a question. So given the suboptimal code generation, vectorization without the special constructs, so looking at what you achieved using the constructs, but also seeing that vectorization is automatic at 03, do you see a negative performance impact of using 03 with auto-vectorization? Is it possible? Or is it just bloated code but the same performance characteristics?
I didn't actually do any measurements on performance. So it's possible that some of that code, it looks pretty messy, but just 'cause it looks messy doesn't mean it's slow. And it would be a code size issue. I think probably more than a performance issue. I don't think you'll go any slower.
But 03 is fine for loading.
Yeah. So depending on the length of the loop and depending on what the overhead of the extra branches are, it could go slower. So there is an infrastructure inside GCC to do cost models. I don't know if they're implemented right now for ARch32, or they're not used really for ARch64, I know that. So this is something, I don't know for ARM or for Linero to look into for a roadmap item, is to do cost model analysis and make sure the cost models are correct. Yeah, similar. Pretty much, it's similar for almost all compilers in terms of cost models and yeah.
All right, so we're over time. So, well, Charles, you have one more comment?
The Neon instruction set has quite rich support for data at different alignments. So the need to assume aligned looks like a bug to me.
Okay. I don't know if that's just conservatism.
Just one more thing, you can also give some information to the vectorizer on your loop with expressing a constraint on the loop and using the built-in unreachable. And with that, you will give more information and hopefully have a better vectorized loop with that. So think of built-in unreachable.
So how would you use that?
Mostly just before your loop, if you know that there is a kind of, how to say that, it's modular, the modularity of your loop. You just have to put a constraint and,
yeah.
Okay, go ahead.
Checking, so for an example is, if you know your loop size is always going to be a multiple of some number, you can put that in front, and you can say if blah, if that, then do built-in unreachable.
Okay.
So there's a few other, and with the infrastructure that was done for the VRP, which keeps the VPR information around until expand time, actually should help the vectorizer. I don't know if it's supported yet, and not necessarily be supported in 4.9, but it will be supported, I think, in 5.
Yes.
Okay, so we did not get through all the topics for today's session, so we didn't get to cover minimizing global symbols, section garbage collection, and GNU symbol hash. We are likely to return to these topics on Next Connect, so we are planning to do another one of these sessions. Thank you very much, and next one is lunch.